Good morning. Today is the beginning is a convocation. I do want to clarify a little bit if that has been confusing. This is the first time we've ever run every Monday programming at King, so a lot of times we're going to have something simply listed as convocation, and often the convocation will be something that is in-house. It'll be something run by people who are here at King, like Mrs. Pollard last week ran the event for people who had done internships. We also have events on Mondays that are associated with something called the King Institute for Faith and Culture, and I am the director of that institute. My name is Martin Dotterweich. We bring in a number of speakers, both from local areas and also from outside, and these are people who are part of the curriculum of King. But there's no test and there's no quiz. This is simply an opportunity to engage with people who have worked very hard on various things and who have something to say. We're going to have more of those events coming up. Next week, we will welcome a King graduate called David Painter. David has a remarkable career at King. Not only is he our only Rhodes Scholar, which means he won a scholarship to go to Oxford University after graduating from King. He then worked for many years for the U.S. government, for the Department of State, Department of Energy, and then taught at Georgetown University. He is one of the world's experts on the Cold War, and he's going to come address us. In addition to being that, though, he's also in the Sports Hall of Fame. He was part of the 1969 basketball team that had great success here at King. On October the 7th, we welcome David Zoll. David is somebody who takes the riches of theology and makes them relevant to Christian living in a way that few others do. He's a remarkable speaker, and I hope you'll join us for him. So we have more events coming up for the Institute, and for those events, again, usually we're bringing in somebody from outside. Today, though, is a special one because this is something that goes back to about 1959 at King, called the Student Lecture. Every year, at the end of the academic year, faculty will select 2 rising seniors to do a lecture about something that interests them during their senior year. We also do this with faculty. Those of you who are rising seniors will be asked to vote on 2 faculty members to do a talk on something of interest to them. And it differs. Sometimes it's the thing that the person is studying. Sometimes it is something very personal. Sometimes it is something unrelated to either. But it's a great chance to hear from one of our own, somebody who has given a lot of attention to a subject and who believes that it matters. Our speaker this morning, then, our fall student lecture, is Christian Jones. He's going to tell you more about himself as part of his talk, which really steals my thunder in the introduction. But I am delighted that Christian is going to be our lecturer this morning. And it's a good morning for an academic lecture about the stars, because today is, after all, the fall or autumnal equinox. This is the moment this afternoon where night and day are of equal length, something that people since the ancient world have noticed as they watch the night sky. The night sky is something that is there as a cause for study and as a cause for wonder. And in both those respects, we find, I think, the mission of King University, to try to find here the things that make us interested, the things that help us succeed, but also the things that excite curiosity and wonder. And for that reason, I'm delighted to welcome today King University senior Christian Jones.
All right, so first off, I want to give a big thank you to the King Institute for Faith and Culture. I'm fine, thank you though. Particularly Dr. Dotterweich for inviting me to speak here today. And I should also mention, since you wanted me to, it's Frodo Baggins and Bilbo Baggins' birthday from Lord of the Rings. So it's even more notable a day because of that. So many of you guys know me based on my astrophotography and astronomy work here at King. And I'm here to mostly talk about that because I know that'll be way more interesting than some sort of national security topic that I could totally conjure up, but it might be a bad time for that, even though right now is probably one of the best times to talk about national security. So I'll get to the astrophotography that I mentioned, but as I've been tasked to teach you guys a little something as well, since there's so much I can talk about, I'm going to tell you guys a little bit about the research that I've done here at King. How I, as someone not in any STEM programs, got there and why it all matters. Consider this, I guess, kind of a science seminar of sorts, except I'll try and break it down for anyone here that isn't an astrophysicist. But I'm not Bill Nye or Neil deGrasse Tyson, but I'll kind of try my best. So at first I should introduce myself. So my name is Christian Jones, and I'm a senior here. I'm graduating in December, and a lot of the freshmen here won't know who I am, which is kind of a tragedy, honestly. So I'll give a brief background of myself. I'm a cybersecurity and information technology specialist working in cyber defense for the Tennessee Air National Guard. And although the big Air Force tends to change the job title a lot, I think I'm really just a client systems technician, or something else that doesn't sound nearly as cool. But cyber defense is what I originally went into after my active duty tenure, which I was formerly active duty at bases in Mississippi and Texas, and in total I've been in the Air Force for about 8 years. So it took me a while, since I'll be 28 this year, but around 23 to 24 years old, I finally realized it'd be a smart and a fantastic idea to go and get a college degree. So I came to King University with no particular degree program in mind, much like a handful of folks probably in this room. I knew I wanted to be a physicist or an astronomer, but I knew being an astronaut was well beyond my abilities as well, so, But King didn't have an astronomy program, and I also knew that I was terribly bad at calculus. Differential equations look like an uphill battle with Greek symbols, and I tend to procrastinate a lot, so that would not allow me to win. Physics was not a tangible option for me either, so I quickly switched to something I knew that I was good at, and that was studies pertaining to intelligence analysis, since I'd already sort of done this work as part of my job in the Air Force. I met Professor Helt over there, sitting, hiding, and asked her a long list of questions in her office, and then I decided that I'd make the switch. And by the way, since she's in the audience here, if you would stand. You don't want to stand? Why not? It's embarrassing. Yes, thank you. You nominated me, so I have to do that. Anyway, intelligence analysis, if you like my Department of Defense there with the tape on it. Funny to some, maybe. Funny to all, I don't know. Anyway, intelligence analysis, that was my lane that I found here. So I declared my major in security and intelligence studies here at King. Ever since I joined the program, I've been subject to a wealth of invaluable information on how to inform policymakers such that they can make the right decisions based on the happenings in the world. Meanwhile, with the Air Force, I've been to Japan during this past summer's Iranian nuclear deterrence operation, which meant I got to do some really cool stuff that I honestly can't really talk about either. So, but I've been to Washington, D.C. several times. Other than that, to the Pentagon on behalf of the Tennessee Air National Guard. I've traveled to Mississippi for training and different schooling classes over the summers. And I've also traveled around the country for various research conferences for reasons both in and beyond the SIS program here at King. So with my background out of the way, I should cover how I solved the problem of still participating in STEM and astronomy, since I hadn't just forgotten about it. It took me 2 entire semesters before I realized that there was actually an observatory on the campus, mostly because the sign on the building was obscured by a bunch of bushes. And get this, you'll never believe this, but there's a campus map. It's even on a brick sign behind McClellan Hall. You might have seen the observatory, at least now, because the bushes are gone. It's across East Cedar Street behind the CAF. I think I got a laser here, actually. It's right there. Little 3 right there. That's the observatory, so it's across the street. So if you didn't know where it is, you'd know now. There were these big, gangly trees. You might see them here. These right here, which would cover your car, and tons of different pine needles in every single crevice that's available. So the actual inside of the observatory was pretty all right, although it was a little outdated, and the shed behind it contained a very large and usually pristine telescope mounted to a robotic arm called a German equatorial mount. And that was a little dated and worn too, and frankly, in my opinion. So I'd never in my life used a telescope beyond what you pick up at a Walmart, some awful looking instrument with cheap knobs and weird, twisty thingamabobs all over it that looked like a big mess of, I just don't really have time for that. So I call those telescopes hobby killers, and a lot of other astronomers also call them hobby killers. So by a show of hands, how many of you have used one of these telescopes before? I'm sure at least someone in this room has. You have, you guys have. I see a few other hands here. So yeah, you'll use it for like one night, and then you'll kind of just put it away forever because you think you just don't have the patience of a saint or something. Or you just can't find the stars through the telescope, or your back and neck will hurt after an hour. And plus, it's like 10 p.m. by the time you look at the clock, and you've not seen a thing interesting except for the moon. I mean, those telescopes work, but they are designed to be cheap. They're usually small, and if you're lucky to see anything at all, the reality is it's probably not actually you, it's your telescope. Almost none of us have the patience of an astronomer from the Renaissance, and if you do, you're probably lying to yourself. So the best telescopes are electric for a lot of reasons, and we are blessed to have a very high quality one across the street today. But I digress. That observatory across the street 3 years ago needed a little bit of work, so I decided to meet with Dr. KK, a wonderful professor who has since moved to other opportunities, and who also selflessly sat with me for many, many hours trying to teach me calculus that I still can't remotely do by myself without a calculator. So he was persistent, but I'm not very math-minded, so his help was very, very kind of him. I realized that, where was I? He seemed to be the person in charge of the observatory. So I came to realize that the building was unused after COVID-19, and that forced students into a more remote work environment for most of their classes. So the observatory had no director like it historically used to have, and Dr. Ray Bloomer had retired years ago, which is fine, no problem. But I felt that for some reason compelled to make use of a facility as valuable as that. So I kind of made it my initiative to turn it into my little fixer-upper project, and let me tell you, it was pretty hard. I had to talk to a lot of people to get that place fixed up, and there's absolutely no way that I could have done it by myself. I had to enlist people and be super, super, super persistent about it, because the reality dawned on me, if I didn't know it was there, a lot of other people probably didn't either, map or otherwise. And I'm very grateful for everyone's help, because every single person who exhibited any interest at all helped in some sort of way to get the place back in working order, and I can't possibly name them all, so I'll name the biggest helper, which is Tom Rutherford. So, many of you probably know him from physical science or astronomy 1 and 2 classes in Whitehall, or I suppose now in general physics among other classes. He is now the director of the Burke Observatory, which he gained roughly 2 years ago, sometime after all of our renovations began. He and I worked hard to get the place operational, painting old iron and steel, pressure washing concrete, building and replacing some computers, programming and calibrating the campus telescope, and before we knew it, he and I were out in the frigid cold December nights collecting data with other students, freezing to death at the telescope so he could teach us how it all works. So I kind of went from just trying to pass my classes in my freshman year straight into national security, astrophysics, and astronomy as a sophomore. This is all kind of the purpose that I found, and I did not have much of a drive going on before that, to be frank, but that's the point of college. If you've heard about the idea of vocation on campus yet, I think I've found 2 things to add to my vocational toolbox alongside cybersecurity, so to speak. It's kind of crazy how self-improvement just kind of works, right? So I've got some other cool stuff to talk about. So what was I actually doing at this observatory once we got it all running? Well, Professor Rutherford wanted us to search for exoplanets first. So exoplanets are a bit different from planets as most of us know them. See, they're called exoplanet because they are outside of our solar system and they orbit other stars. In fact, most stars in our galaxy and probably in every other galaxy in the universe are expected to have planets of some kind. We, and by we, I mean humans, have observed enough of these worlds to know that they are way more common than we once thought. Here's an artist representation of some different types and sizes of exoplanets that have been observed by mankind. I was asked to observe one of these, and it's really not as straightforward as you might think unless you're really just into photographs that look like TV static or a bunch of featureless dots. And for reference, that is Jupiter right there, and that is Saturn. So these are the sizes of all these exoplanets that have been discovered. A lot of them are pretty big, some of them are super small, and the ones that are super small we can't really detect. So if you look at this image, that's a field of stars. Around one of those stars, there's a planet, and we did actually take this image. This was one of the first exoplanets we observed. How in the world do I know that, though? Well, a much more expensive telescope owned by NASA detected an exoplanet there first, because it's actually extremely hard to be the first discoverer of an exoplanet without a space telescope to operate. You can do it from the ground, but it's pretty arduous work, and it's, frankly, astronomically expensive, pun intended. So Basically, I'm not necessarily discovering a planet at all, but what I am doing is checking that NASA's enormously expensive taxpayer-funded telescope in space did actually detect an exoplanet in the first place, rather than an asteroid or a cloud of hydrogen gas or something else moving in front of a star. We're confirming that they exist by detecting them whenever NASA says that we can detect them based on a carefully calculated schedule determined by some averages in the statistics of their data. So how? Right, well, this is where it gets a little bit harder to understand, and I'll try my best to explain it in a way I think all of us can comprehend. You see, we can't really magnify on a star like you might think. It just isn't possible without a titanic budget in the big B billions of dollars. We just don't have that capability. Really, until the last few months, there haven't been any telescopes that could pull off physically seeing an exoplanet through magnification alone. That stuff is kind of like optical magic. So I'll explain a little more. So have you ever stared straight into the headlights of a car while you're driving? You know those really bright, awful headlights that blind you at night? Imagine the high beams are on and you're just staring into them like it doesn't even hurt at all. You're like, I don't know, a quarter mile away, just sitting there, and the car with those awful headlights is also just sitting there menacingly. And then right in front of the car, a gnat, as small as could be, flies perfectly over the headlight bulbs. That gnat, even as small as it is, just blocked the tiniest amount of light from blinding your eyes, and you probably didn't even notice it. These Mark I eyeballs aren't great for detecting things like a camera is, and so that's where a camera comes in, a photometric camera, meaning a camera that can scientifically measure the photons impacting the sensor. So now imagine the same exact example, but replace the headlights with the sun. So which two planets are between the Earth and the sun? And I know this will be cheating if you answer Mercury first, so which is the remaining planet? Literally anybody can answer, just somebody. Venus, thank you. Thank you. So Venus and Mercury, that's right. So we can actually point a telescope at the sun, and by the way, just don't do that unless you know what you're doing. But the sun, that's our bright, blinding headlight all day long. It's blinding us right now through that window. So Venus and Mercury are just like the gnat. If you have a telescope designed for looking at the sun, you can actually watch Venus and Mercury perform what's called a transit, where they pass across the entire face of the sun from one side to the next, like that gnat did with the headlight. So you'd never know it unless you had a telescope and a lot of safety precautions, because it kind of hurts to look at both headlights and the sun. So this is exactly what we're doing with an exoplanet. It just hurts a lot less when the star is really far away. So exoplanets transit the face of their own star, just as Mercury and Venus do with the sun, and we try to detect that transiting motion. But let's add one more factor, that bright headlight, move it all the way to Knoxville. Maybe even move it all the way to Los Angeles in California, or even further. It's a really, really bright headlight powered by nuclear fusion, and then with that photometric camera that I mentioned, you measure the average of how bright that headlight is. When the gnat flies over it, or rather when the planet moves across the face of the star, you keep on measuring, and that tiny, minuscule sliver of light that was blocked, well, that, my friends, is your exoplanet transit. So a whole world, maybe even covered in people like you and I, or a bunch of Ewoks from Star Wars, or Na'vi from Avatar, or something like that, I don't know, might be out there. Ewoks and Na'vi actually live on the moons of gas giants in those movies anyways, so maybe one of those exoplanets has a habitable moon, or something potentially habitable similar to Titan and Europa in our own solar system. All the planets we have detections of at the observatory are, well, gas giants anyways, like I said. All that this information tells you, though, if you stuck with me through this awful analogy of gnats and headlights, is that this stuff is not easy or cheap. But there's a very serious point to this all. Finding planets that orbit other stars proves that our star system isn't unique in that it has planets. The observation of gas giants so massive and so close to their stars also tells us something else. Not every star system forms the same way that ours has. There's a chance that something could have influenced the way that our star system formed to support life on Earth, and perhaps it's an indication in support of divine predestination to form Earth, or the story supporting creation theory. Of course, solid exoplanets like Mercury, Venus, and Earth, or Mars, have also been detected in other star systems as well. But for now, there has been little to no indications that any of these types of exoplanets could support life just yet. It's really just a bunch of hopes and dreams, although I think it is inevitable that we will one day locate a potentially habitable exoplanet, and that is the ultimate goal in the search for exoplanets. At least for now, the pale blue dot, as Carl Sagan would call it, stands by itself. So with that out of the way, the Berg Observatory has a pretty good telescope, actually, that can detect Jupiter-sized exoplanets with relative ease. Yes, these are all Jupiter-sized, meaning basically every planet that we detect is very, very large, and probably also uninhabitable because the planet is gaseous with a small, hot, rocky, or metal core surrounded by tens of thousands of kilometers of toxic, hot, or compressed gas that will destroy the human body in every way. So this object on the screen is actually the first exoplanet that we detected, and that's an artist representation, of course. This is called WASP 104b, named after the telescope that initially discovered it. And just for the sake of time, the 3-second summary for this graph is that the little hump in the chart is the detection of a planet orbiting the star WASP 104 because the star, well, it got dimmer as we observed it. That particular planet is very interesting because it's mostly comprised of potassium and sodium, making it the darkest exoplanet ever discovered, as it absorbs 97% of all impacting light. So this planet is mostly entirely midnight colored, if not for the fact that it also orbits so incredibly close to its star that it turns red and orange from the temperature. In fact, it orbits so close to its star that it's closer than Mercury is to our own sun. That's all according to NASA, so they've got all that information. So that's pretty cool, right? Since I'm a little kind of pressed for time, I'll end my explanation on how exoplanet detections work there. So I liked doing this stuff so much that I decided to build my own telescope. And there it is. It costs a lot of money and a lot of time. It's red like a sports car because red makes it fast or something like that. I mean, seriously though, in astronomy, fast means that it collects light a lot quicker than other telescopes. So you can look at something for less time and get a better picture than somebody else when it's faster. And some of the DMAD students in here probably know and appreciate what I mean when I say the aperture is 61 millimeters and its f-stop is 4.9. It's like a permanently open shutter for your camera, and I can image whatever I want to in the night. So seriously though, this is one of the fastest telescopes that you can put together, and it's just red because I like it that way. And I put an American flag on it. It's cool. America. So. All right. I originally got this thing to do astrophotography with, a type of photography dedicated to photographing objects in space, which is different from the science in that these pictures don't look like TV static, they actually look pretty. Turns out King's telescope needed some maintenance on that German equatorial mount that I talked about, and we got to get a new one. So while we were ordering a new robotic mount, which took a while, we had to do some research on something. So my hot rod telescope or whatever is literally like 1/10 the size of King's, if even that, and no matter how fast it is, it just can't detect super faint objects. A faint object from my telescope is one of those Jupiter-sized exoplanets we detected with King's telescope. At least that's what all the science, we couldn't detect it, and that's at least what all the science for the last 100 years seemed to tell us. And that science was, well, mostly correct. So it just couldn't do it. But none of that science really considers the efficiency and sensitivity of a modern camera. So, well, I decided to just start imaging some exoplanets that we had seen before. And so guess what? It detected some of them. Just barely. These graphs aren't as good as the other, but the leftmost graph represents a pretty good detection. The rightmost two represent detections, but with some differences, unlike a perfect full detection. The middle graph had some clouds that drift in while I was imaging. That happens a lot and just ruins my whole night. And that obscured the star, so you can see where all those little red X's are. That's where the clouds came in, and I mean, by that point, it's not really a full transit, it's just a half transit because, you know, it got interrupted. Anyway, so this other one as well, it's only a half transit because there's trees that are really tall over there, and when it drifts into the trees, you just got to stop imaging. And so all the data beyond that point just got cut off, and so I left it out of the graph. So basically, we proved that if you spend a whole lot of money, you can image exoplanets even with something about the size of a really big Stanley Cup when you put a photometer on the back of it. So we've imaged a total of 15 exoplanet transit events, some of these targets multiple times, although we haven't yet combed through all of the data to produce the graphs because it's frankly really arduous and a lot of the programs we use just won't work with what we've got. So we'll get that sometime before November. So after detecting these, we took some of our work to the American Astronomical Society and presented our findings in Washington, D.C., and in this January we'll be going to Tucson and Arizona with some more of our findings as we finish up the last stretch of data processing, hopefully by November. But this is good stuff. I recommend at least one of you guys in here, literally just one, to get into astronomy. Especially anyone in a STEM field here. If you're in physics, that's great. The opportunity is literally right across the street, and most of you guys live here in dorms on the campus, so you can build your resume, you can travel. King will usually pay for the travel also. It's great. If you want to try this out, just let me know. You won't have to modernize a whole observatory to do it. I've already done that for you. We're even going through the effort of redesigning the way the observatory operates so that we can hopefully someday operate it from indoors or remotely from the other side of the planet. That would be awesome. You can do it from your phone. All right, so I've got some other cool stuff for anyone wondering how I can somehow tie this into national security. So if I've got time, which I have a little bit, check this out. So this slide kind of looks like a military photograph. Well, it kind of is. Some people might even say that, oh, that's a UFO. That's aliens. Well, no, not really. I decided to do a project with the Department of the Air Force to see if a telescope you can build at home could be used to photograph spacecraft and solve any kind of metrics about those vehicles. So I did exactly that. And the short answer is yes, you can, but this was actually very hard also. However, on my third try, I finally got these photos. And this is actually a really cool one because that's Jupiter. I tried to see if I could get this satellite to go straight over Jupiter, but it just barely missed. But this is like a pretty awesome picture, I think. Anyway. So this is a spacecraft called Tiangong, and this is, of course, a render of it. It's not real. Did anyone know that China owns its own space station separate from the International Space Station? Well, there it is. It's a streak of light in my photograph because it's really tough to get a still image of something at orbital velocity. And you also really can't get any usable scientific data on that if you don't know what you're doing. So China has their own space station for some frankly disgusting reasons, basically because they commit various crimes against humanity. The United States banned them from accessing the International Space Station. So trust me, they had it coming. So I basically took 3 images of their spacecraft, drew angles to the points in space Tiangong was at based on where I was, and I scanned them with a government program from the National Reconnaissance Office that I also can't explain, which was once used for tracking Soviet spacecraft, and I plugged in my geocoordinates, which were exactly at the Carmack gate at the entrance of King. John Martin, this is you. Yeah. He's the one holding this antenna next to my laptop. So the program gave me some integers that I could plug into an equation, and I found all of that in an orbital mechanics manual from the 1990s, and eventually I figured out the velocity of the spacecraft. If you know its velocity, you know its altitude because it's in space and it's in orbit. It's not going to just come back down. This stuff was pretty hard to do for a guy, though, that doesn't know a lick of calculus and didn't take any calculus classes, but fortunately we have calculators, and I love calculators. I'm sure all of you also do because they just get you through your class. So they make us look really smart. Anyway, I did a whole bunch of stuff with this at some regional research conferences, and I had some handy helpers like John Martin Harbaugh and Faith Woodson, who have since graduated. They helped me set up equipment and held some other instruments while we did additional, less successful experiments that were involved. And I know that's kind of vague, but if I explain the whole project, we would probably never leave convocation. So so we confirmed, in fact, that you can measure this stuff probably from your backyard, apparently wherever you wanted to, in fact. You just have to have a cool telescope with an American flag on it, I would hope. And you probably want to measure other countries' satellites and not the United States satellites, because, it's cooler. All right, so I still have pretty pictures to talk about. So, like I said, I bought that telescope for astrophotography, and admittedly, it's what most of the people in the room who do know me for. So I like to take pictures of things that are out in space, and while these aren't going to be Hubble Space Telescope or James Webb Space Telescope photos, they're pictures from mostly right here in Bristol and just right across the street. So here's most of the best photos I've gotten, except for this first one, which is my first ever photo. It's really bad. It even looks even worse on a projector. So this is the Orion Nebula. This is supposed to be something that you just take a picture of and it just works and looks fantastic. Well, this does not look fantastic, so let's move on. So this is the moon. I took this with one of the pictures that I borrowed from the library, or the cameras that I borrowed from the library. They've got one in like a closet over there that you can just check out, and yeah, it takes good pictures. It's a camera, so, I took a sweeping, panning picture of the moon, and then this final one is actually with my iPhone through the telescope, so you can just use the telescope with your phone mounted to it, and it just works just as fine as a normal camera if you're looking at the right stuff. So this is Jupiter. You really can't see it, but there's two moons right here. I don't know which moons those are. There was a moon like way over here in the picture, but I can't really show you those two moons if I were that zoomed out. So that's Jupiter. You can see all the bands on it. It looks pretty cool. That's Saturn. It's blurry. That's just what you get with the telescope. So this is the Pleiades. This was one of the first pictures I took after I got my own telescope finished when I was building it. So this one's a color image, which is cool. You really can't see anything either because it's on a projector in a sunlit room. This is the Andromeda Galaxy. You can see the disk here. I swear it looks better on my computer screen. This is the Orion Nebula. So that first picture I took that looked really ugly, this is what it's supposed to look like as you take an image of it. So I think this one looks great. This is one of my better pictures. It's usually one of the better pictures that any astrophotographer has because it's just a one-shot image and you really don't need to edit it. It looks good as it is. But this one's cool. It's an emission nebula, and you can see where it's been lit by stars either in the background or within the core of the nebula, which is that bright center that it has. So this one is a cool picture. Wish you could see it better. But there's a lot of galaxies in this picture. I took it because this is a frame that has this place called Bode's Galaxy and the Cigar Galaxy. This is Bode's, and this is the Cigar Galaxy. When you look at it from the side, it has a little band that makes it look like a wrapped cigar. But there's actually a lot of galaxies in this picture, and I've used this at some elementary schools to try to explain to students there how many galaxies there actually are. So you can point your telescope anywhere and there's galaxies somewhere, but for you to actually see them with most telescopes, you need galaxies that are close by and pretty bright. And these are how many galaxies are actually in the picture. Every little circle is a galaxy and it has its associated name there. And if you start looking at the fainter ones, they just start turning into numbers because that's by the time we realize that there are so many galaxies in the universe that you just have to start numbering them to get by. So some of them have cool names. One's called Holmberg, Bode's Galaxy, Cigar Galaxy, and that's the end of the named galaxies there. So I also went to Indiana to see the total solar eclipse. I think this was like 2 years ago now, actually. So we contacted through Candace Sutherland. She's a teacher at Tennessee High. I think she retired now. But she had a friend up in Indiana that owned some property with a lake, with ducks all over the place, and this cool little weird shed thing that you get under. So we just set up a little camp, and so that's also John Martin Harbaugh there with some sunglasses on, or his solar glasses so he doesn't go blind, looking up at the sun, looking cool, and that's Faith Woodson sitting back there. So this is the picture of the eclipse that I got. It was pretty phenomenal. I mean, it got physically cold around us when this thing happened, and you had a horizon 360 degrees all around you because the shadow is acting like the sun is setting. And because the moon is so perfectly shaped to cover the disk of the sun, you actually can see these jets that extend off the surface of the sun. So these are these gigantic plasma jets that I think you could fit the Earth inside of this plasma jet, which I thought was pretty cool. Mostly everybody from this area got these pictures of these plasma jets. Some showed up better than others, and I think I got them pretty good. So you can barely see what's going on there. That's just a galaxy, so it's purple, looks cool. You can see all the hydrogen gas and all this kind of stuff. The core of the galaxy, it looks pretty good. I got a solar filter, mostly for the total solar eclipse, and you can see some sunspots. So these sunspots were actually the ones responsible for the aurora that we could see. Was this last year, I think? I think it was last year that we had like a seriously big aurora that extended all the way down past Tennessee. So if you went outside and you could see that the sky was pink, this was your culprit. It was this big group of sunspots. So I had perfectly gotten my solar filter just in time to take pictures of those, which were really big, and you can also fit the Earth inside those sunspots too, so, so they're really big. So this was in Washington, D.C. When we went to one of our conferences, there was a brief moment in time where Mars was really close to the moon. And so I didn't take these with my telescope. I took these with this thing called a plane wave, it's like $50,000. It's really cool. But you can see Mars right there. It's really tiny. You get a little bit of orange, and you can still see the moon in pretty good detail. So it was a really good picture. I don't know. Then a lunar eclipse happened. And you can see that from here in Tennessee. So this was actually right across the street. I set up, and I had gotten a nice laser, and I can take these cool pictures with this laser that I've got in my hand because I mounted it on my telescope. And you can see that the moon's all orange, red, and then the pictures that I got from that are really good. So this was the first image before the eclipse started. I have gotten it good enough to where you can see some, it looks almost blue in some of these craters, and then there's a lot of rustic looking color. So if you've heard in the news the moon is rusting or something, well, it does have rust on the moon. It's got iron oxide, but you can kind of see that a little bit right up in here. It's a little brown. And this is when the planet started to cast its shadow onto the moon. You can see this blue kind of curvature from the atmosphere. So you can see where the sun is shown through our atmosphere, and it's casting this blue shadow onto the moon, and then there's the orange and red from the sunset that is also on the sides of the planet. And this is the final picture where it's mostly red and blue. It kind of looks like a firework pop, I think. All this blue up here from the atmosphere, and then there's some red. Apparently some people could see green in this at some point during the eclipse, and you have to do some pretty exact editing to get there, but this is what I got. But I also took this picture in Nevada at the Valley of Fire with Dr. Moyer, which is really pretty. It was an awesome morning. So anyway, if you guys want to do stuff like this, please send me an email. My name is Christian Reeves Jones. You can just find me in Outlook, and we'll work on something. I promise you that everyone in this room could do something similar if you really put your mind to it. And if there's enough interest, maybe I'll even make a group me. We can do an observatory tour. You can join the astronomy club as well. Just give me your student email after this if you want to stick around. But even if you don't, I just want to ask everyone in here to commit to something as well, because it's what got me here today. Just be curious, seek growth, and have some wonder. I'm a firm believer that people who are persistent will succeed in life. Not everything will just land in your lap. So you must, and I implore you, you must ask questions. Even if you think it's a stupid question, even if it's something that a professor will have to repeat, even if it's something that you should have learned in grade school, ask about it if you don't understand what it is. And I know college isn't easy, it's stressful, it takes a lot of time, and if it isn't hard yet, it totally will be at some point. But you just need to stay persistent to succeed, and it's your persistence that you'll need to push with to develop resilience. So maybe while you're here, you'll even find an exoplanet while you're at it. So thank you guys.